Amplified geochemical imaging is the world's leading-edge surface geoscience tool for measuring and mapping of hydrocarbon compounds, for petroleum exploration and development, mineral exploration, and environmental site assessment. The concept of microseepage is important to the vertical migration of hydrocarbons. With microseepage, the reservoir seal is still effective, but the reservoir pressure and high hydrocarbon concentration creates a strong natural driving force. While the reservoir seal is effective in holding more than 99% of the hydrocarbons, the seal is not completely impervious. Grain boundaries and micro cracks throughout the overburden provide pathways for the movement of the hydrocarbons to the surface at rates of meters per day. Amplified geochemical imaging technology can be applied as a tool to reduce risk and cost in many different areas because of its very sensitive and rich compound dataset and the improved analytical procedures. Over the last 10 years, over 2,500 surveys have been conducted, both onshore and offshore, in nearly 100 depositional basins. The surveys were conducted in all climates to evaluate the hydrocarbon potential of structural, stratigraphic, and salt traps. Over the years, significant advances have been made to the technology. Initially, the range of compounds measured was increased to C20, including pristine and phytane, followed by improvements in laboratory throughput and baseline detection levels. In 2007, new software development made improvements to hierarchical cluster analysis, which allows the technology to identify specific hydrocarbon phases. This slide attempts to show the relationship between geological parameters like soil composition, water content, and sensitivity plotted against hydrocarbon compounds and sampling time relative to the surface geochemical sampling techniques. Traditional techniques, including direct soil analysis, active soil gas measurement, and microbial, are limited to sandy soils and C5. Also, the measurement of methane can skew the interpretation because it is ubiquitous and often from biogenic sources. By comparison, the amplified geochemical imaging dataset is robust and rich with measurements of hydrocarbons up to C20 and sensitivity to part per trillion. The passive sampler, developed by Gore, contains specially engineered hydrophobic adsorbents encased in a microporous, expanded polytetrafluoroethylene membrane. This membrane, known as Gore-Tex, has pores engineered small enough to prevent the blue soil particles and water molecules from entering. The red gas molecules, about 1,000 times smaller, are unimpeded in their path to the adsorbent. This allows the modules to be placed directly in dry or water-saturated soils, and even in water depths up to about 10 meters. The samplers are easily deployed by inserting them into narrow-diameter holes, pounded or drilled into the ground to a depth of about 0.6 meters. Field installation and retrieval is fast, easy to accomplish, and low cost, and allows economical deployment over difficult terrain with no disruption to landowners or the environment. The collector is left in the ground for a period of 17 to 30 days, during which it passively collects volatile compounds in the soil and vertically migrating gas from the reservoir. After the retrieved samplers have been reconciled, a very sensitive, state-of-the-art analytical method is applied that incorporates thermal desorption, gas chromatography, and mass spectroscopy. Compounds in the nanogram levels are detected in concentrations as low as 1 part per trillion. Over 150 volatile compounds can be measured, as needed, for the different applications. In oil and gas exploration, 85 compounds are detected, including normal, iso, and cyclic alkanes and aromatics. These are direct hydrocarbons. Molecules, smaller than ethane, are not adequately retained by the absorbent, but natural gas with greater than 99% methane can still be mapped by looking for the higher alkanes always associated with this gas. The laboratory data set for all analyzed compounds are provided to the client in an Excel spreadsheet format. There are two different methods used to interpret the laboratory data set. The first method is the hierarchical cluster analysis, where the samples are grouped into clusters based on chemical similarities. This chart shows a cluster analysis for a survey conducted in West Siberia. The samples are listed along the vertical axis and the compounds C2 to C20 along the horizontal axis. The black slashes denote samples planted around the dry and gas condensate model wells. The red areas indicate high correlation between the sample and the compound, while blue indicates low correlation. Note that the cluster analysis in the lower portion of the chart denotes a gas condensate signature, and the central blue portion of the chart indicates background or dry signature. These two areas show strong correlation to the two model wells. The upper portion of the chart is interpreted as a very strong oil signature that was unknown and unexpected in the area. This graph shows the oil signature from the previous slide of the cluster analysis. Note the strength of the signal in nanograms on the vertical axis. Based on the drilling of the exploration discovery well, followed by a 3D seismic program, it was estimated that this signature represents approximately 340 million barrels of recoverable oil in a reservoir at a depth of about 3,000 meters. The second method of interpreting the data set is called discriminant analysis. By modeling the two wells that represent the dry and productive end members of the exploration target, the separation of the groups is used to define the chemical difference. In three-dimensional space, the center of the dry model samples and the center of the productive model samples are defined as 0 and 100% probability of the targeted hydrocarbon phase. The survey grid samples are projected into a probability line connecting the two end member model wells. Using either one or both interpretation methods, a probability map is created to identify areas of high hydrocarbon potential trapped in the subsurface. Only under very unique and controlled circumstances will the technology determine the quantity of trapped hydrocarbons. In this example, oil is trapped along the upthrown east side of a north-south fault. 3 structural closures have been mapped with 2D seismic on the downthrown side of the fault. The oil kitchen is located to the west. Before drilling a well, how do you know if any of the mapped structures contain hydrocarbons? A surface-amplified geochemical imaging survey answered the question and identified the structure with the highest probability of trapped hydrocarbons. Subsequent drilling confirmed the interpretation. If you think of a world where your technical team could determine the probability and phase of the trapped hydrocarbons before the exploration well is drilled, and if you think of a world where your technical team could estimate the areal size of a discovery before the drilling of the delineation wells, then you are thinking of a world where amplified geochemical imaging is part of your technical toolbox.